it should be clear by now that if your vector field is conservative, that's a really great thing for you computationally speaking. It will knowing that your vector field is conservative will help allow you to simplify a lot of the calculations. But in order to do that, we also need to know the potential function. So the purpose of this video is helping to identify, okay, how can you tell that your vector field is conservative? And if your vector field is conservative, how can you determine a potential function for it, which the potential function is the thing that will allow you to easily compute vector line integrals by what we just saw in the fundamental theorem for vector line integrals. And so here is going to be our component test for conservative fields. So suppose that F is our vector field. We're writing it as M is the coefficient I hat, N is the coefficient J hat, P is the coefficient K hat, where M, N, and P are all functions potentially, no pun intended there, of X, Y, and Z. So suppose that this is our vector field, an open simply connected domain, whose component functions have continuous first partial derivatives. Then F is conservative if and only if we have these three equalities of partial derivatives. And the thing here is that sometimes we call these the cross partials. Cross partials derivatives are equal. Why is that? So let's take a look here. This first equation says the derivative of P with respect to Y is equal to the derivative N with respect to Z. So N is the coefficient, N here is the coefficient J hat, N is corresponding to Y, P is the coefficient here of K hat, P is corresponding to Z here. So N corresponds to Y, P corresponds to Z. We have these cross partial, sometimes we'll call this the equality of cross partial derivatives here. M corresponds to I hat, P corresponds to K hat, M corresponds to X in some way, P corresponds to Z. M corresponds to X, P corresponds to Z here. The partial derivative M with respect to Z is equal to the partial derivative P with respect to X. And then finally here, the partial derivative N with respect to X is equal to partial derivative of M with respect to Y here. M corresponds to X in some way, N corresponds to Y. And so this is our component test for a conservative field. So you have a conservative vector field if you have a vector field on an open simply connected domain, most of the time we'll have that. Although we will do one example where we don't have that. How to tell your function here is your vector field is conservative if all the cross partial derivatives are equal. By the way, let me just point out that if you have a vector field that is only living in 2 dimensions here, so you only have M I hat plus N J hat, and I guess also you'd have to get rid of the Z variables here. So N of X, Y times I hat plus N of X, Y times J hat, then these 2 conditions are deleted. How to tell your vector field R2 is conservative? You only have one pair of partial derivatives to check for equality. Okay, so this shows us how to determine whether or not our vector field is conservative. But then the follow-up question is, well, let's say that we have checked and have determined that our vector field is in fact conservative. How do you find potential functions? And the answer to this is that you need to integrate the components of F with respect to X, Y, and Z respectively. and combine. Okay, so let's take a look here at this example. Find a potential function, if possible, for f is equal to 2xy plus 5, x squared minus 4z, and negative 4y. So first, let's figure out whether or not this is, in fact, conservative. So first off, this is defined everywhere in R3 and everywhere in space. So the open simply connected domain, that's all going to check out here. This is M, this is N, this is P. So what do we have to check? dp dy is equal to dn dx. The partial derivative of P with respect to y is equal to the partial derivative of n with respect to z. I think I may have said x there instead of z. My apologies. So the partial derivative of P with respect to y is negative 4. The partial derivative n with respect to z is also negative 4. So that checks. Then we need the partial derivative m with respect to z needs to equal the partial derivative p with respect to x. So the partial derivative of m with respect to z is 0. And this needs to equal the partial derivative of p with respect to x, which is also 0. And that checks. So by now you should be seeing the correspondence here that it's the partial derivative of the function in the x slot with respect to z needs to equal the partial derivative of the function in the z slot with respect to x, cross partials. So finally, the partial derivative of n with respect to x needs to equal the partial derivative of m with respect to y. The partial derivative of n with respect to x here is 2x. Partial derivative of m with respect to y is also 2x. So this checks, and so this shows us that f is conservative. So f is conservative, we know that. So we know there must be a potential function. How do we find this? We integrate components of f with respect to x, y, and z respectively and combine. So what do I mean by this? This is a little bit of a careful thing that we have to do here. We need to do this very, very carefully. So we're looking for a potential function, little f of x, y, z. It needs to equal the following three things. So all of these are going to be little f of x, y, z. So it needs to equal, first we're going to integrate the first component of big F here, m, with respect to x. And then it also needs to equal the, we need to integrate the second component here, n, x squared minus 4z. We need to integrate this with respect to y. And then finally, we need to integrate the third component here, negative 4y. We need to integrate this with respect to z. So this is my comment here about we need to integrate the components of f with respect to x, y, and z respectively. So what do we get when we calculate out these antiderivatives? So let me just say there's a couple things we have to be very careful about. So pay close attention to this. So we're integrating this with respect to x. And so we would end up with x squared y plus 5 times x. But then there needs to be a plus c. But what about this plus c here? So usually we think of this plus c as a constant. But this isn't going to be here. This doesn't have to be just a constant. This can be any, I'm going to call it c1 because there's going to be c's and the second and third antiderivatives here. But it doesn't have to be just a constant. It can be a function that depends on y and z, but can't depend on x. So take a look here. Integrating with 2xy plus 5 with respect to x gives us x squared y plus 5x plus some function that depends on y and z. Why do we have to include this as a function here? Well, if we take the partial derivative of this with respect to x, partial derivative of x squared y will give us 2xy. That's good. The partial derivative of 5x will give us 5. That's good. And the partial derivative of any function with respect to that depends on y and z, but not on x, the partial derivative of this will be 0. And so to be the most general that we can be, we need to write it like this. Okay, so let's now integrate x squared minus 4z with respect to y. So this will give us x squared times y. This will give us minus 4yz. And then we have a c2. But now our c2 isn't going to be a constant. It's going to be a function that potentially depends on x and z, but can't depend on y. Okay, finally, integrating negative 4y with respect to z gives us negative 4yz. But then we need a plus c3, where this c3 can depend on x and z. Okay, so this is what we've got here. Now we need to combine. And I'm using this word combine carefully here because common mistake here is people add together all of this to get the final answer. We don't want to add it together. We want to combine. Let me show you what I mean here. So we want to locate terms that are located in all of these. So let's see here. X squared y. Let's put that x squared y down here. There's an x squared y down here. Let me explain what I'm doing here. F of x, y, z is equal to this. It's also equal to this. It's also equal to this. We want to figure out right out as explicitly as possible, and part of that will be figuring out like C1, C2, and C3. So we see that f of x, y, z needs to have an x squared y, needs to have an x squared y. Well, do we see an x squared y down here? Well, this is an x squared y. Oops, I made a mistake. That wasn't supposed to be an xz, that was supposed to be an xy. X squared y is part of this. So x squared y, and the x squared y, and down here lives in here. So that's why this is showing why that needs to be a that needs to be a function of x and y and not just a constant. What else do we have? 5x. Do we see a 5x down here? Well, 5x depends, can be part of the C2 x comma z here because it doesn't depend on y. 5x, do we see a 5x down here? 5x can also be part of the C3 here because there's no z dependence. Okay, what else do we have? Oh, I see a negative 4yz. Negative 4yz down here. Negative 4yz also goes in, it can get combined into the C1 of yz. And then finally, we need a plus c here, an overall constant, although if we want to pick a particular potential function, we can just cover up the plus c. This is a particular potential function. So this is the work that we have to have in order to find a potential function here. Let me point out, common mistake is that sometimes people just add, and so they'll end up with like 2x squared y or a negative 8yz. No, that's not how this works. Okay, so we combine, we don't add together. And you can check for yourself. Well, actually, let's just go ahead and check this real quick. If this is f of x, y, z is equal to this, the gradient of little f is equal to the x partial derivative is 2xy plus 5. The y partial derivative is x squared minus 4z. And the z partial derivative is negative 4y. And that exactly matches what's here. So that's the process of finding, a potential function.